Thanks, Araceli.
Thank you very much for the introduction. Thank you also to the organizers for this opportunity. I'm going to talk about non-anonymous fiber nodes, and this is a joint work with Mario Udave Muñoz and Enrique Ramírez Lozada. So let me start with something about the composition of node stereo. So suppose you have a K is a node in a tree and F a cipher surface for K. So if you take a regular neighborhood and we represent by this as a transversal view or left, we can consider the three manifolds obtained as the complement of a regular neighborhood of the cipher surface in the exterior of K. And this three manifold has a boundary composed by an annulus A and two copies of the cipher surface F minus and F plus. So we know that M has a Higard splitting with boundary where we start with the cipher surface, we attach some one handle and obtain the Higard surface S, and then we have to attach two handles to come back to the cipher surface F plus. When this Higard splitting is weakly reducible, which means that there are compression disks one on H1 and one on H2, but they don't intersect each other. This means that this Higard splitting is weakly reducible. When we have this situation, we can change the position of one handle and two handles, similarly to the work of Charlemagne and Thomson for closed tree manifolds, to obtain a Higard decomposition as follows. So here we start with F, our cipher surface. We attach some one handles, then obtain a Higard surface S1. Then we attach two handles and obtain another cipher surface S2, and so on. So we have many Higard splittings where each one of these pieces, H1, well, let me call this H2, etc. These regions are compression bodies. Now we identify again the copies of F, and we will get a circular decomposition of the exterior of the node that we represent with this picture. We start with the cipher surface F, and then we attach some one handle to obtain Hegar surface S1, then we attach some two handles to obtain another sized surface F2, then attach again one handle to obtain another Hegar surface, and so on, until we come back to the first surface. Since in every step, when we attach one handle, we increase the genus. We will say that the Hegar surfaces will be called as 6 surfaces. And when we attach 2 handles, we decrease in genus, so we will call these surfaces as thin surfaces. Here we have some definitions about complexity of surfaces. If we have a closed connected surface, we define its complexity as 2 times its genus minus 1. When the surface has non-empty boundary, we first cap off the boundary component with disk, and then compute the complexity of the capped surface. And when we have the sphere S2, we define its complexity as 0. And when we have a disconnected surface, we define its complexity as the sum of the complexities of the component. For a circular decomposition in the exterior of K, we define the circular weight with respect to that decomposition as the set of complexities of the 6 surfaces. And then we order these numbers in non-increasing order. For 2 decomposition, we compare the order multisets lexicographically. We will define the circular width of the exterior of K as the minimal circular width over all possible circular decomposition for the exterior of K. And we will say that the exterior of K is in circular thin position when the circular width of the decomposition is the circular width of the exterior of K. Now we are going to classify the nodes in terms of the size of the circular width. So if the size of the circular width is 0, we will have a fiber node because it doesn't have a thick level. And when we have just only one thick level and also one thin level, we will say that the node is almost fiber. And when the size of the circular width is greater or equal to 2, we will say that our node is non-almost fiber. So this was a briefly description of a work of Fabiola Manjarres in 2009. She proved the following theorem. which says that when we have our knot in circular seam position, then each one of the Hegarde splitting is strongly irreducible. Each seam surface is incompressible, and each thick surface is weakly incompressible in the exterior of K. And as a corollary, we have that if K is non-almost fiber knot, then it has to at least two disjoint non-isotopic incompressible cipher surfaces. This is because if our knot is non-almost fiber, then it has at least two thick levels. So it also has at least two thin levels. Sorry. Because of this theorem, each thin level is incompressible. It's an incompressible cipher surface. So we have this result. Infinitely many examples of almost fiber knots are known. The only known examples of non-almost fiber knots are the connected sum of non-fiber knots. We will construct a family of hyperbolic knots, which are non-almost fiber. Here is a remark. Consider that P is a genus 1 surface with one boundary component, and take this product region, T cross an interval. So let T be an annulus on T whose core is an essential core in T. Then C cross I is a solid torus. This blue region. So we are going to make a surgery by replacing this torus by another solid torus in such a way that C cross 0, this annulus, is identified with an annulus in the torus R, which goes around 2 or more times longitudinally in the boundary of R. So it can be shown that this space is a genus 2 handle body. And the schematic version of this attach is this. Here we have the annulus region between the T cross 0 and T cross 1. And this blue circle is the solid torus attached to the product region. Now suppose K is a knot with the following properties. There are 4 cipher surfaces for this knot, and all of them have genus 1. each region between two of these cipher surfaces is a genus to handle body, as in the remark, as this construction. The core of the annuli CI cross 1 and CI plus 1 cross 0 intersect in one point. So that means that if each of these regions has the composition, as I mentioned before, like this. So remember that here we have an annulus which represent a closed, essential closed curve in the cipher surface. So this property tells us that this closed curve, which comes from H1, intersects the closed essential curve, which came from H2. So these two essential curves intersect in one point on T2. And we will prove that there exists an infinite family of hyperbolic nodes, K of L, M, N, which satisfies the above property. So for the proof, consider this diagram where each one of these boxes has the numbers that indicates of horizontal crossing, and L, the absolute value of L, M, and N is greater or equal to 3. And let's see that the node L is trivial. This is because this crossing here cancels with the crossing here. And by canceling this crossing, we will obtain this strand here. And by twisting this crossing, we can eliminate also them. So L is the trivial node, and we can see that also the node K prime are trivial. So if we consider the double branches cover along L, we will obtain that the covering space is S3. And we note also that the linking number of K prime and L is an odd number. So the pre-image of K prime is a node on S3, and we will call it K of L, M, N. And this is the family of nodes we are going to prove that are known almost 5. Now, let's see that if we take these 4 disks in the exterior like this, okay, like this, we will have that each one of these leads to a cipher surface for K. This is because their boundary is parallel to the knot K prime and intersects the knot L in 3 points. So it has to lead to a genus 1 surface, and the boundary is K, so they are genus 1 cipher surfaces for our knot. And also note that each of these cipher surfaces are non-isotopic to each other. This is because if we consider this tube, the region inside here, we will see that it leads to the solid torus air in this representation, which is glued non-trivially. So this cannot be a region product, and then the cipher surfaces are non-isotopic. So we have proof that our knots, our family of knots, satisfies this one and this one properties. So now let's see that this annuli intersect in 1 point. So to see that, consider this disk, which contains 2 intersection points of C2 with the knot L, and consider another disk containing these other 2 intersection points. So we see that the boundaries of this disk intersect in 2 points. So when we lift them, we will have 2 annuli intersecting the boundaries in 4 points. But if we take just the core of them, we will have that they intersect in 1 point. So we have proof that this family satisfies these 3 properties. Now, let's see that the exterior of our knot admits circular decomposition of width 3, 3. Remember that this is the complexity of the 6th level. So by anisotropy of the diagram, we can move in this way. And if we consider this position, we will have the green disk, which intersect the knot L in 5 points. So this disk leads to a surface of genus 2. and the red this leads to a genus 1 cipher surface. So what happens here is that when you move the disk in this direction, we will see the intersection, and we will see how the genus 2 surface change to a genus 1 surface. So this means that in this critical point, we have to attach two handles to reduce the genus. And if we do the same, but we pass from a genus 1 surface to a genus 2, in this critical point, we have to attach one handle, and so on. So this gives us the composition of the knot, such that we have here a thin surface of genus 1, then one of genus 2, then again genus 1, and then a thick surface of genus 2. And this is just attaching one handle, then a two handle, and then one handle, and a two handle. So this composition has width 3, 3, because the genus of these surfaces is 2, and its complexity is 3. Our main theorem says that there exists an infinite family of genus 1 hyperbolic knots, which are not non-almost fibers. And the sketch of the proof is that we have constructed a family of knots, K, L, M, N, which have genus 1, and the exterior admits circular decomposition of width 3, 3. So we suppose that they are almost 5, and then the exterior must admit a circular decomposition of width 3. We need some lemmas. The lemmas is the knot case is hyperbolic. The second one is that on each region, on each genus 2 handle body, we have isotopy, just 5 incompressible annuli. This is the schematic version. The third lemma says that if we have an annulus who's with one boundary in, let's say, T1 and the second boundary on T3, then we can isotope this annulus to be parallel to the boundary of the knot, or to lie in just one side of this region. And the last lemma says that the exterior of K cannot contain another genus 1 cipher source. So I see I don't have much time. So let's assume that the exterior of K has a circular decomposition of width 3, and then it means that we have this decomposition with one big surface, which we call sigma, and we analyze how sigma intersects the cipher surfaces P1, P2, P3, P4, and these surfaces divide sigma into some pieces. For the lemmas, for the previous lemma, we cannot have regions with adjacent annuli. So the only possibilities of pieces are these. So in the proof that the exterior of the node cannot admit the composition of width 3, we have to analyze these 6 cases. Sorry, I forgot to mention that here, each of these regions means that sigma intersects with the region HI. So I have to stop here. These are the 6 cases. So thank you very much for your attention.
Thank you, Araceli, for your very nice talk. Thank you so much. Does anyone in the audience has a question? Okay, so let's thanks Araceli again.
Thank you very much.